Hello all of you, welcome to the 7th lecture on the course on analysis and modeling in chemical engineering. In the last class, we started talking about the fundamental laws and principles in chemical engineering, and we discussed the idea of equation of motion and transport equation. In this lecture, I will now extend to other things which are material balance and energy balance, and in the following lecture, we will cover the other concepts that is down the list. So, this is the equation that you cannot forget as the chemical engineer, and you may have encountered this in every undergrad chemical engineering course that you have taken, and that is simply the input minus output plus generation is equal to the accumulation. If I am talking about a batch system, then I am talking about, let us say, mass in minus mass out. And if I am talking about continuous system, then I am talking about the rate of mass in minus rate of mass out plus generation, whatever, right? But this equation fairly is the same that we use, whether it is in terms of mass or the rate of mass flow. And I can also define it, instead of mass, I can talk in terms of moles. I can talk in terms of overall number of moles, or I can talk in terms of moles of a particular species in the system. Again, the equation pretty much remains the same. And in fact, the same equation I also use for balancing energy. The energy coming in minus energy going out plus the generation of energy in the system is equal to the accumulation of energy in the system, right? So, you have seen this in when we look at, for example, chemical reactors, and the same equation when you look at, for example, separators like distillation column, and fairly the same equation in every chemical engineering problem that you basically have. In fact, if you think about it, this equation is a general equation that applies to things other than chemical engineering as well. Let us say, for example, if I am doing it on the amount of money that I have, that again is like fairly the same. It is like how much I get as a salary at the beginning of the month, and how much do I spend on things, and then within the month, what is my extra income that I can generate, and let us say how much money I can keep in my bank account and save it for the future, right. So, this is a fairly general idea of conservation that we use a lot in chemical engineering, but it is not something limited to chemical engineering itself. It can be applied to many different contexts. So, I will take couple of examples using this idea of material and energy balance, but let me do a quick recap on one of the problems that is using the fundamental concept that we have covered in the previous class, just to keep you in line with the sequence of things that we are covering in this course. So, in this problem, we have a colloidal dispersion that is consisting of uniformly charged spheres of a certain radius r and a certain charge q, and it is dispersed in an almost neutral solvent. The Coulomb force, that is the electrostatic force between the two spheres at center to center distance d, is given by F proportional to q square by d. The dispersion may be considered stable if the spheres do not precipitate to the bottom due to gravity. I already have told in the last class that electrostatic interactions can basically be more dominant, and in fact, that is what will stabilize the suspension. So, I want to develop a fundamental model to determine the minimum charge q, which would result in a stable dispersion as a function of relevant model parameters, right. So, of course, there are many details in the problem, but there is something that we can at least do to begin with, a simplistic kind of a model of what must happen in order for the suspension to be stable, right. So, let us imagine for simplicity that there are only two major forces in the system. One is the gravity and other is the electrostatic force. Of course, there are viscous forces, there is buoyancy force and things like that, but just to demonstrate the idea, I am beginning with a case when there is a balance between only two forces, the Coulomb force and the gravity force. And in that case, my q square by d should essentially compensate for mg, right. I can of course make the model more complicated or include more details by, for example, adding the buoyancy force and viscous force and all that, but these are probably the most important parameters in the system, right. So, at least Q should be much larger than, let us say, under root of mgd with whatever prefactor that we have here, because I told you that the Coulombic force is actually given by something like this, 1 by 4 pi epsilon epsilon, and q square by d, by the way, is the definition of the, not the force but the energy. So, therefore, the force actually is q square by d square, right. So, we need to now slightly revise our idea, because earlier I was talking in terms of like energy. So, now let me keep force on both sides. So, let us slightly revise our estimate and say that q is given as something like mg under root d and under root 4 pi epsilon naught epsilon, right. This is what should happen at the bare minimum level, right. Now, going forward, if we want to see like how exactly we will find this d, what is the distance between the particles, what will it depend on. So, let us say, for example, if it is uniform suspension, then the particles are just everywhere, right. So, let us say you have a certain density of particles in the system, then on an average one particle is going to occupy a small volume that is of the order of the distance between the two particles, right. So, what I am trying to say is that we know that the d is the distance between two particles, right. So, a particle may have a particle on all of its side, but on an average the room that is available to the particle where it can freely move is of the order of d, and I am telling it in the order of magnitude, not a precise value. It will basically scale as d, or the magnitude will be something close to d, maybe twice d, half d. That is not very important when we look at the order of magnitude estimate, right. So, within that small volume that is occupied by this single particle, the density is rho is equal to 1 over d cube, because we have only one particle in the volume, something like d cubed, right. So, this d will then be something like rho to the power minus 1/3, right. So, the advantage of changing this distance to rho is that if I am doing an experiment, let us say I am looking at a glass of milk, I cannot tell what is the distance between two particles within the milk, but I can probably tell what is the density of those particles in that milk, or the density of the milk, and I can probably take it from there, right. So, density is a quantity that is easier to define. I am talking about density of the particles in this case. Density is more easier to define than the distance, and in fact, the particles will actually move in the fluid. So, it is not that the distance will remain constant as such, but the density will overall remain constant, right. So, therefore, I can now replace d with rho to the power minus 1/3, and we have something like q scaling as under root mg rho to the power minus 1/3, and then whatever 4 pi epsilon naught epsilon that we have, right. So, I can go ahead and include more details, but the point which I was trying to make is that for a colloidal system, the equation of motion is applied very differently, or the force balance is applied very differently than compared to the ball falling under gravity in a viscous liquid, and let us say the granular flow down the hopper, right. Let me now come back to the idea of material balance, and let me now take an example where we will use the idea of material balance in addition to the idea of equation of motion. So, I am taking a rather simple problem. You have a tank containing some liquid, and at maybe in the beginning of the experiment, you punch a hole at the bottom of the tank. So, the liquid will start to leak out with a certain volumetric flow rate, and we want to figure out how the height of liquid in the tank is changing with time. Let us say this is the problem that we have. But what I want to do here is, of course, in fluid mechanics course you have learnt about Bernoulli equation, and you may have the temptation to use Bernoulli equation, or if you are really inclined towards fluids, you also know about Navier-Stokes equation, that is in fact more complicated, and I would say with fewer assumptions than compared to Bernoulli equation. But I will avoid that temptation, and I want you to draw the expected profile of this height as a function of time. You will begin with some height of liquid in the tank before the hole was punched in, and with time, so height is going to be a function of time, and eventually all the liquid will drain out, right. So I want you to draw an expected profile of this height versus time based on the physical intuition without doing any kind of a derivation, and then I want you to define the appropriate control volume and write the mass balance for this particular problem, right. So let us first try to draw the profile. So one thing is very clear, that height is going to decrease with time, right. That is something like, without even a knowledge of fluid mechanics, we know that if I punch a hole, the liquid will leak out of the vessel of the tank, and therefore the height is going to decrease. That is not something that is very difficult to see, right. But now the question is that how it is going to decrease, right. Recall the example of time to travel. I knew that the average velocity of the vehicle is a function of traffic density, but what is the nature of that function? So I want to kind of do a similar kind of intuition in this problem, whether it is going to be something like a linear decrease, let me call that 1, and eventually of course the height will go to 0 because all the liquid will leak out, or it is going to be something like maybe this. That means in the beginning you have a bigger slope, and at the end you have a smaller slope, or you have something like this, where in the beginning you have a smaller slope, but at the end what you have a larger slope, right. Which one of them is more likely, 1, 2 or 3, right. And now again, based on the intuition, you can see that okay, you have a tank that is full. In the very beginning, the fact that the tank is full is going to give rise to a large leakage to begin with. That should give you a very high slope in the beginning. In the end, let us say when very tiny amount of fluid is left, then that tiny amount can actually come out rather slowly, right. Of course, we will derive it later, but that is kind of an intuition we can probably gain even without writing any equation, right. So probably something like 2 appears to be more likely, right, and we will see like why it is so. Okay. So now I want to write the material balance for this problem, and I have a certain height at t at a certain time, and I have a small orifice, and from there is a volumetric flow rate qt, right. Now the question is, what is the velocity of the fluid here? Let me call that velocity as some v, and the velocity of the fluid at here, let me call that as something like v naught. How different are going to be these two velocities? And again, let us imagine that the leak is fairly small. Of course, from the leak the flow will be continuous and you will have a certain velocity, but from the top the change in the height of the layer will gradually change with time, but you will not see this kind of drastic difference if you observe the tank from the top, right. At the bottom you will see a dramatic change, something is leaking out, but from the top you will barely see anything happening of that effect, right. In fact, most people will not even know, if they don't look at the bottom, that something is leaking out, right. There is a way to formally see that, and that is my continuity equation, and that tells me that the net volumetric flow rate at the top is equal to the net volumetric flow rate at the bottom. So let us say there is some area of cross section A naught here and some area of cross section A here, then the net volumetric flow rate is A naught V naught at the top and something like A into V at the bottom through the orifice, and therefore the V naught is something like A by A naught of V, right. And now it is not, I would say, difficult to assume here, and that should be the most common case, that this A naught is going to be much larger compared to the area of the leak A, and therefore, V naught is going to be very less compared to V, and therefore, it does not harm so much if I assume that the V naught is 0, right. So, now I will define this entire thing as the control volume or the system. Of course, there can be velocity variations in the tank, but I can assume in the simplest possible model that there is not much change within the tank. Of course, the tank level is going down, but if I look at the velocity, it is fairly equal to V naught here, 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 or anywhere along the height of the tank, right. It is not such a bad assumption, and in that case I can write the material balance over the entire liquid in the tank, right. So, wherever I am writing this material balance on, that becomes my control volume in this case. Of course, when I am interested in the spatial variation of velocity, then I can define the control volume to be much smaller, something like a small part of this tank and things like that. But here I am not interested in the spatial variation of velocity within the tank. So, I assume that everywhere in the tank the velocity is the same, and that is equal to V naught, and that V naught is anyway assumed to be much less than V. So, I am assuming anyway that the V naught is something close to 0. So, in that case, if I do a material balance, I can do something like the rate of inflow minus the rate of outflow plus the generation is equal to the accumulation. If you look at this problem, there is no input, no water is being added in the system, but there is an output. That output is the volumetric flow rate Q, which is minus Q, and there is no generation, no water gets generated in the system, right. So, whatever water is there, that is there, of course, it is leaking out, but there is no generation of water, no new water is coming in the system, and the accumulation is not there, no water gets accumulated over time. Actually, it is reverse of accumulation, water is getting depleted over time, and that is given as something like the area of the vessel, which is A naught into dH by dt, right. The other way to look at it, it is d by dt of A naught H, because A naught H is the volume of the liquid in the tank, and I am not considering any density change of water and things like that. So, therefore, I am not considering density anywhere here. If I want, I can multiply both sides by rho, but they will cancel anyway, right. So, this basically tells me the dV by dt in the tank, how the volume is the tank is changing, and that is given by the volumetric flow rate there, right. So, clearly dH by dt is negative. So, therefore, we have a negative sign there. So, this becomes the material balance for the system. The A naught dH by dt is equal to minus Q. Okay. So, this was the problem that we had. So, we have identified the control volume and we have written the mass balance for the system. In fact, I wrote a volume balance because the density was assumed to be constant, but density times volume is mass. So, in this case, we do not have to consider density. Now, what I want to do is I want to now derive the expression of this height of time for these cases. What I am essentially doing is proposing different kind of empirical models, mathematical form of how the Q, the volumetric flow rate coming out of the tank, may depend on the height of the tank, right. Until so far, I have not used Bernoulli equation, I have not used any physical laws. I am developing some kind of an empirical model along the lines of what we did for the spring dashpot problem. I am proposing some empirical model, and I already have the intuition of how the HT versus T should look like. It should probably look like number 2 here. So, maybe I can possibly be able to figure out which of these may be more likely, right. And then I want to do it for a constant case, a linear case, a power n case for n higher than 1 and less than 1, and then I want to see what will happen if I put n equal to 1 in the expression of 3 or 4, and whether we recover the expression in 2. Intuitively speaking, whatever we get for this case, if I put n equal to 1, I should get that case, but let us see what does the math give to us, right. Okay. So, we have already figured out that my q is equal to minus a naught dh by dt, and let me do the first case where I am assuming that this q is some constant. Let me call that constant q naught. So, in that case, what we have is my a naught dh by dt is equal to minus q naught. So, I can move this a naught on that side, and I am going to get minus q naught by a naught there. So, h is going to be, in the beginning you will have some h naught minus q naught by a naught into t, right, a linear function in t. And now you see how it should look like. The ht versus t from this model should look like something like this, beginning with h naught and eventually going to 0, right. Of course, the equation itself tells me that it can be negative, it can continue this way, but we know from the physics that the height cannot be negative. Once all the liquid is gone, there is no point solving the problem, right. So, now let us look at the second case, q proportional to h, and in that case we will have dh by dt will be something like, now I can say q is some k into h. So, if I plug it in there, I will have something like minus k by a naught h, right. And if I move the h to the left hand side and integrate, I am going to get something like ln of h between limits h naught to h of t is equal to minus k by a naught t, and this will give me h by h naught is equal to exponential of minus k by a naught t. That gives me an exponential decay of the height as a function of time. That may be a function something like this. So, this will be the case 1 and this is case 2. That seems more likely based on the intuition that we had earlier, but let us go ahead and try to find expression for the other cases. So, now I will do the third case where q is proportional to something like s to the power n as was stated in the problem, and in this case we are going to have dh by dt something like minus, we had q naught by a naught there. So, I can again assume a function q is equal to some k h to the power n. So, we will have minus k by a naught s to the power n, and then if I integrate, we have h to the power minus n dh is equal to minus k by a naught t, where the left hand side has to be integrated with the limits h naught to h, and this will give me something like h to the power minus n plus 1 by minus n plus 1 with the limits h naught to h, which is equal to minus k by a naught t, and that gives me something like h minus n plus 1 by minus n plus 1 minus h naught minus n plus 1 by minus n plus 1 is equal to minus k by a naught t. That expression is the same for n greater than 1 or n less than 1. So, the same applies for case 3 and case 4. Well, let us see what will happen if I put n equal to 1. And you see there is a problem that if I put n equal to 1, the denominator there, it becomes 0. So, I have infinity. I can try to sacrifice it, or I can try to save it by moving this minus n plus 1 on the other side, but that will not help either, because then the time dependence will go away. And in no way it is going to give me the exponential relation, right. And the reason why this happened is because I was talking about integration of 1 over h dh that gives me a ln, and that ln you will not get in this particular case. So, for n equal to 1 case, we need to treat the integral separately, anyway, right? So now I have this kind of a relation, and again I can see what will happen for n less than 1 and n larger than 1, although it is not very intuitive to plot just from looking at this equation, unlike the exponential case that we had earlier. So now I am taking some experimental data that we have, where we look at how the height is changing with the time. The typical experiment, you can imagine that you have some cylinder and you paste some graph sheet on the cylinder. You can do this experiment very easily yourself. Take any plastic tube or something, put a tape, and then put a graph sheet and see how the height is changing with time, right? The tube has to be transparent enough, and then you should have a stop clock to measure the time. So now, of course, you can imagine that I can do the experiment multiple times, and this is the data for 3 sets of experiment, right? The experiment is done in this particular way. So we start from some height, let's say 8 centimeter. So I will measure the time it takes to go from 8 to 7. So I will stop the clock when it becomes 7. That is the time right here, 11 second, 8 second, 9 seconds that we found in 3 experiments. Then we do the same thing for 6 centimeter, then for 5 centimeter, and I keep on doing it, and I get 3 measurements of time, right? So I want to do this, and I want to fit that with the experimental data. So I already have the expression for all these cases. I will take the last case where I had this n, and I will try to fit it and see whether it works or not, right? And then I can compute the error and obtain the parameters of the constant. And what I also want to know is, are there any disagreements from the experimental data? So let us do that. If we do that, we will have the following. So my height versus time. So I am showing here for 3 sets of data, which are shown by these markers here in the plot. And this dashed line that you see, that is the fit from the equation we derived for h to the power n case for a value of n equal to 1 by 2. So purely empirically, we obtain that the last equation we derived, where we assume that the q is proportional to h to the power n, works best in this case, and we will get a value of n equal to 1 by 2 purely by empirical means, and these are the parameters. You can try out the experiment yourself and see what do you get. By the way, this should be A naught in the description we had. Okay, so now finally I want to go back and compare that with what do I get from the Bernoulli equation, right? So how do I apply Bernoulli equation in this case? So in Bernoulli equation we have P by rho plus V square by 2 plus Gz as constant. That is a statement of Bernoulli equation. I am not assuming any viscous terms and things like that, the standard Bernoulli equation. And now I will apply it between this point and this point, the top and bottom of the tank. I am assuming the tank is open, so pressure is the same here and here. So the pressure term will be same, P naught by rho on this side, P naught by rho on the other side. I already have said that the velocity of this can be assumed to be 0 by the continuity assumption, continuity equation, and so we have a 0 here, but we do have a height which is gh for the top, but on the right we have g into 0, which is 0, right? But the velocity here is something like v square by 2. Velocity here is v square by 2, right? So we do have cancellations, and what do we get? We get v square is equal to 2gh, and therefore v is proportional to square root of h. And you may imagine that the volumetric flow rate is equal to my A times V. I have defined this as area A and this as area A naught. A times V, which is also proportional to square root of h. So therefore, we have basically established what we have just established using the empirical equation, right? So it demonstrates the idea of equation of motion, it demonstrates the idea of material and energy balances, and finally it demonstrates both kinds of model, an empirical model and fundamental model in this case. I can go ahead and try to look at other problems, and this is one of the examples, again from something not to do with chemical engineering, but just to demonstrate the idea of material balance. So, let us say for example, I take a train from Delhi going to Dehradun, and there are multiple stations on the way of the train, and I want to write the material balance and energy balance for the train, not for any particular purpose, maybe just for fun, and try to see like what are the relevant variables that is there, right. In fact, I can do that. I have to make certain assumptions, but I can do that. So, let us say for example, the train contains some n compartments and is stopping at some S stations, and there are certain components of the train, and I am talking about people as components, maybe passengers, vendors, train staffs and whatnot, right. And then I make some assumptions, so only people are being considered as components. The system will never quite reach steady state, people will keep on boarding and deboarding at stations, and there may be movement of people between compartments in a typical Indian train. I am assuming it's electric train, not very important, but nonetheless let us assume that. And then I also assume, similar to the kind of assumption that we made in the traffic example, is that the average speed of train is v between the stations, right. Of course, the train has to stop at the station, so there is going to be deceleration near the station, and train need to accelerate after the station, and there will be some acceleration period. But if you look at a longer run, we can say there is some average speed between the two. In fact, the speed may also vary when it is running, depending on the mood of the driver or whatever is the traffic restrictions imposed by the authority. But nonetheless, you can imagine that there is some average speed, and I can ignore the effect of acceleration and deceleration. And then we can say that, of course, the people may have different mass, weight. So, we will say that there is some average mass and there is some empty mass of the train. So, the train mass is the mass of the people and the mass of the train itself. Of course, there is a mass of luggage and things like that that we can ignore. Okay. So, then I can define my system as made up of an engine and then multiple compartments, and I can define the number of people in a certain compartment of type, let us say K. This is the number of people of type K. Type can be standing for passengers or vendors or staff in the compartment I, right. So, if I look at any particular compartment, let us say compartment number 2, people may come here from compartment number 1, and people from here can go to compartment number 3. In fact, it can be a positive or negative movement. So, if they are coming from 1 to 2, I am calling it positive. If it is going from 2 to 3, I am calling it positive, but the reverse movement is also possible, then it is negative. So, I can define the flow rates of people coming from compartment I minus 1 to compartment I, and going from compartment I to compartment I plus 1. Positive when they are going out to I plus 1 and negative when they are coming in, and same we can do it here, right. And then between stations there is another flow rate, that is how many people are boarding or deboarding the train. If it is boarding, it is positive. If it is deboarding, it is negative. Clearly, it is typically 0 except between the stations, unless somebody is jumping on and off the train. So, this is mostly 0 except when it is stopping at a station, and in this case as stations, right. What I want you to take from this example is how I am using this notations in a manner that kind of become kind of a consistent or a general kind of an equation, rather than writing separate equation for compartment 1, compartment 2 and so on, right. So, I am writing it for compartment I, and that is the general form of the equation. Of course, for compartment 1, from engine there is no flow. So, we may write separately for the first compartment and the last compartment, but anything in between I can write the same equation that I have. So, I have a general form that is written in a manner that the same equation can be applied irrespective of the compartment except the first and last one, and irrespective of what type of passengers I am looking at or what type of people in the train I am looking at and things like that. So, then I can go ahead, write the material balance. This is the number of people that is coming into the compartment at stations, then coming into the compartment from the other compartment, this is the number of people going out of the compartment, and this is the net accumulation of people in the compartment, which can be positive or negative. Positive if people are increasing in the compartment, negative otherwise. There is no generation here unless somebody gets born on the train. That's very rare. So I'm excluding the generation term, but we do have an accumulation term, and I can write this equation for all the compartments and all the type of people in the compartment, right? And in fact, the point is try to show you like how the idea is very general as opposed to for a particular system in chemical engineering. I can also write maybe an energy balance, and in this case it can be used to compute the power required to drive the train, and that should be a function of the kinetic energy, the empty mass of the train plus the mass of all the people in the train, right? That becomes the total mass. Total mass into v square by 2 gives me total kinetic energy, and how the kinetic energy changes with times gives me the power, right? And the total mass of the people is found by summing the number of people in compartment I of a particular type K. So, I am summing over all the types of people and all the compartments, right? So, we can write the energy balance and mass balance for the train. In fact, if you have learnt about it, you may recall that there is a tank in series model for reactors that is somewhat similar, at least analogous to this problem. So, we can in fact draw analogy for whatever model we have developed here for the tank in series model, but the idea was to demonstrate you that the material energy balance concepts are quite generic, need not be limited to chemical engineering. So, with that I want to summarize here. So, we discussed the idea of material balance and energy balance, and in the next class I want to go ahead and talk about other concepts, other fundamental concepts in chemical engineering. Thank you so much.